Alright, we're going to see if this series converges or not. Well, first of all, it's a good idea to put this into the summation form with a sigma and also come with a formula for the an. So let's do that. First of all, let's just go ahead and write down the sigma right here, and n goes from 1 to infinity because it keeps on going forever. Now, let's see. It looks like everybody has the ln2 power right there, right? And everybody has a 1 on the top, so we have 1 over, and notice that this is like 1 to the ln2's power, which is just 1 anyway. And all the base right here, they are changing. 2, 3, 4, 5, and so on, starting with 1 right here. So it's just n to the ln2 power like this. So that's pretty much the form for it. And now this is actually just a p series, isn't it? Because we can look at this right here. Let's write down p is actually ln2. And this right here is approximately 0.693. But don't just tell me the p-value. You have to tell me that the p-value right here is less than or equal to 1. And that means what? That means this right here diverges. Right? So again, diverges by the p-series test. So that's it. Okay, here we are going to look at this series 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125. And this right here, it's actually really easy if it stops right here. But, you know, it keeps on going forever. So there's a plus dot, dot, dot. Alright, so converge or diverge? Well, it's a good idea to put this into the sigma notation form. And let's say n starts with 1 and it goes to infinity. Everybody on the top is 1. And then notice that this is the same as 1 over 1 to the third power. 8 is the same as 2 to the third power. This is the same as 3 to the third power, and so on, so on, so on. So we get n to the third power. So, converge or diverge, is this an easy or hard question? Easy, right? Because this is the p series that we love. Here, p is equal to 3, which is greater than 1. Therefore, this series converges. And if you just put down p is equal to 3 is greater than 1, I know you are using the p series already, but just to be clear, I will write this down by p series. Alright, for the series, 1 over 2 ln2 plus 1 over 3 ln3 plus 1 over 4 ln4, and so on. Does it converge or not? Well, as usual, let's put this into the summation form. Because you see we have 2 and 2 here, 3 and 3 here, and so on, right? It would be a good idea if we let n start with 2 and to infinity. Yeah. And then the formula is just 1 over n times ln n. That's all. And to figure out if it converges or not, we can actually use the integral test. Because we can actually integrate the function 1 over x ln x. And let me just put that down right here for you guys. I'm going to let f of x be 1 over x ln x, and go ahead and provide me a graph. It will look like this. X cannot be equal to 1 because otherwise ln 1 will be 0 and that will be on the bottom, and that's not good, right? So you have this part, that's all. So just mention that f is positive and decreasing and continuous for the x values bigger than or equal to 2. And this is the only part that we care anyway, right? Now, let's go ahead and do the check. Namely, we just have to do the integral. So check. Integrating 2 to infinity. Well, we are going from 2 because n right here starts with 2, right? So just keep that in mind. 1 over x, ln x, dx. Well, to integrate this guy, go ahead and just do u sub. Let u equal to ln x. Du will be 1 over x dx. And if you would like, you can just multiply the x on both sides, and you get dx equals dx is equal to x du. Alright, now here is the deal. Take this integral to the u world. Well, x is going from 2 to infinity. When x is 2, put it here, u will be going from ln2. And when we put infinity to here, ln infinity will be infinity. So that's what we have. And then we have 1 over x. ln x is the u. And then the dx is x du. Right? If you do it this way, you can see the nice cancellation between the x and here, right? So far so good. Continue. Integrating 1 over u in the u world, we get natural log of u. And you don't need the absolute value, but you know it's just a habit anyway. Doesn't really matter. Alright, anyway, and then we're going to plug in, right? So go ahead and plug in. ln2 and also infinity. We will finish everything in the u world. So first we'll have ln of infinity minus ln of ln2. And let me just get rid of the absolute value. I'm so sorry, because we don't need it. It doesn't really matter. It's just Mr. Chow, make up your mind already, right? I know. Anyway, put infinity here, put ln2 here. ln2 is finite, but ln infinity is infinity. All in all, we get infinity. Therefore, this right here diverges. So what does that mean? That means this right here also diverges by the integral test. Okay, for the series, 1 over e plus 2 over e to the 4th power plus 3 over e to the 9th power and so on. Well, does it converge or diverge? Well, it's of course a good idea to write this into a sigma notation form. Notice, when we have 3 here, the power here will be 9. And when this is 4, this is 16, and so on, right? Yes, it's just the square of the number on the top. Yeah, so I'm just going to write it as n goes from 1 to infinity. On the top we have n, and then on the bottom we have e to the n square power. Alright, so good. How can we decide if this converge or diverge though? Notice, if we look at this as x over e to the x square, we can just do integral with that. Yes, so we can use the integral test. So here we go. Let me just write this down here for you guys. I'm going to say let the function be equal to x over e to the x square. And we can let u equal to x squared for a nice u sub, right? So that's very nice. And then go ahead and show a picture. However, the graph for x over e to the x squared does not have a vertical asymptote. It looks like this, right? It looks like this. And you see, the graph is still positive, decreasing from 1 to infinity, right? From 1 to infinity is decreasing. And it's always positive, meaning above the x-axis. So we can definitely use the integral test. So just go ahead and provide me a graph, and looks like this, maybe. And yeah, so this is f, and I'll just say f is decreasing, is continuous, and it's also positive when we have x is greater than or equal to 1, right? So just kind of indicate that. So let's say this is 1, and then we have the numbers here, and so on, right? Anyway, let's go ahead and do our integral. So go ahead and check the corresponding improper integral, meaning we go from 1 to infinity, x over e to the x squared dx. And now let's do u sub, of course. Let u equal to x squared. Well, actually, you know what? Before we do u sub, let me bring this up to the numerator. This is the integral 1 to infinity x. Bring this up, so we look at this as e to the negative x squared dx. Yeah? Okay, then do u sub. U equals negative x squared. Du equals negative 2x dx. And then I will just isolate the dx so we can see some nice cancellation. So we have du over negative 2x. And as usual, take this integral to the u world. We get the integral. When x is 1, we'll go ahead and put 1 in here. We get u is equal to negative 1. And when x is infinity, put this here. We get u is equal to negative infinity. And then just go ahead and continue. Here we have the x, and then we have e, and negative x squared is our u, and dx is the du over negative 2x, like so. And now let's just go ahead and do some cancellations. This and that can be cancelled. Very good. Alright, so now let me just put this right here. First off, we see that this is negative 1 and this is negative infinity. It's kind of out of order, right? Because we usually like to have a smaller number on the bottom. In this case, the negative infinity should be on the bottom, right here. Well, this right here is actually pretty nice because notice that we have this negative 2 on the bottom. But when you have a negative times the integral, we can just switch the order of the integration, right? We can switch the order of the limits of the integration. All right, so what we are going to do is, because of that, we can legitimately write it as integral, and we'll put down negative infinity here up to -1. And I'm just going to put down 1 over 2 in the front. Again, the negative sign is used already to help us switch the limits of integration. If you don't switch it, it's actually fine. You will see that in the end, the subtraction will work out well. Okay, so here inside we have e to the u in the u world. Go ahead and integrate that. We get 1/2. Integral of e to the u is just e to the u. We actually did some work, but it's just the same answer, right? Now, plug in negative infinity and -1. -1 go first. So we have 1/2 e to the -1. And then we are going to minus the second part, which is putting negative infinity. The first part is just going to be 1, and e to the -1, we can bring that to the bottom, so we have 1 over 2e. And guess what? The second part here, e to the negative infinity is just equal to 0. So this right here is just all 0. That means we have a finite answer, 1 over 2e. What does that mean? That means this improper integral converges, right? Because this right here is a finite value. That means this infinite series also converges by the integral test. Well, let's take a look of each term and then come with a formula, and depends on what kind of test that we're going to use, right? So here we go. Right here, let me just put down the sum as n goes from. We'll notice that instead of the inverse tangent on the top, we have 1, 2, 3, 4, 5, and so on. So it seems that we just have to go from 1 to infinity for the n values. And everybody has the inverse tangent on the top, so we must have inverse tangent. And n starts with 1 right there, so that's really nice. It's just inverse tangent of n. Good. Now, let's look at the denominator. We have 2, 5, 10, 17, 26, and so on. We have to find a formula for the denominators. All right. To go from 1 to 2, 2 to 5, the third term, right? The 3 to 10, 4 to 17. I think this right here is a pretty good clue, because we know 4 squared is 16, and we add 1 to it, we get 17. And does that work for the next number? Yes. 5 squared is 25, and we add 1 to that, we get 26. So in another word, the denominator is just 1 plus n squared, like that. That's the denominator. And of course, if you go back to the first one, 1 squared is 1 plus 1 is 2. Very nice. So now, this is the form perhaps that we like much more, and we will just have to see what test that we should use right here, right? And imagine if this is an integral, can we integrate inverse tangent of x divided by 1 plus x squared? Yes, right? So let's just use the integral test. So here we go. We are going to consider the function. I will write down f of x, which is just the inverse tangent of x over 1 plus x squared. And you should show me a graph like on the side right here. And if you graph this, you're actually going to get like this. It goes up from the origin up and then down like that, right? Well, it doesn't really matter because when x is 1 and after that, this function right here is, of course, you can see it's decreasing, continuous, and of course, everybody is positive. So just be sure you include these details. And now, of course, to use the integral test, we have to just do the integral. So let's go ahead and check the integral. And we are going to go from 1 to infinity of the function, inverse tangent of x over 1 plus x squared, like this. All right, now, how can we integrate this, especially if you haven't done integrals for a while? Yes, we can just do a u sub for this, right? So we are going to take u equal to the inverse tangent of x, and we see that du is just 1 over 1 plus x squared dx. And notice that we have the 1 plus x squared in the denominator right here. So the 1 plus x squared here, along with the dx, all this right here will be the du right away. That's very nice. So let's take a look. Keep in mind, these right here are in terms of the x. X is going from 1 to infinity. And when you take this integral to the u world, be sure you also take the numbers as well. When x is 1, we put it here. Inverse tangent of 1 is pi over 4. So we have u going from pi over 4. And then we will put infinity right here for the x. And the inverse tangent of infinity, that's pi over 2. So u will be going up to pi over 2 like this. Now on the top, this is the inverse tangent of x. Namely, it's just the u. And all this right here, the things I colored it right here, let me just color it again in green this time, just to give you guys some Christmas color. This right here is equal to the du, right? So I just put down du right here. And now we can just totally integrate this, and this is actually really nice. Integrating u in the u world, we get 1/2 u squared, and then plug in, we finish everything in the u world. So pi over 4, pi over 2. But if you are not really interested in terms of getting the value of this integral, you don't have to worry about the result. I will still write it down for you, just to be a good teacher, I would say. Anyway, put the pi over 2 here, so we have pi over 2 squared. Actually, let me just do like this, it's easier. Pi over 2 squared, and then we are going to take this and then minus parentheses 1/2 pi over 4, and we square that. Yeah. And just do the math pretty much. This right here on the top is pi over 2. This right here on the top is pi squared, and then over, this is 4 times 2, which is pi squared over 8. And then right here, we have minus, again, pi squared on the top, over, this right here is 16 times 2 is 32, like this. And then, of course, get our little common denominator. I need to multiply this by 4 and 4 minus 1 is 3. So altogether is 3 pi squared over 32, like this. But again, this value, as long as it's finite, we know that this guy right here converges. We are not going to say the answer to this series is exactly 3 pi squared over 32. In fact, we actually do not know how big this series, how big this sum is. We don't know. All we know is that if this improper integral turns out to be finite, in other words, this improper integral turns out to be a convergent, that will tell us that this infinite series also converges. Why? Of course, we did the integral, and that's the integral test. So just write this down right here for you guys. By the integral test. And this is all you need to show. This is all you need to show. I have absolutely no idea how big this sum is going to be, but I just know that it will have to be finite thanks to the integral test. Okay, we're going to see if this series converges or not, and of course it's a good idea to put this into the sigma notation first. And let's go ahead and do that. So here we go. The sum as n goes from 1 to infinity. Notice that on the top we have 1, 4, 9, 16, 25, 36, and so on, so on, so on. Name the n squared. So that's it. And then on the bottom, notice everybody has a square root. So let's go ahead and open that square root. And if you look at the inside here, this is 2, and then 9, and then 28. 28 is like 27, huh? It's like 27 plus 1. 64 plus 1 is 65. And 125 plus 1 is 126. And if we look back, 1 plus 1 is 2. 8 plus 1 is 9. Yes, it's the perfect cube plus 1. So here we have n to the third power plus 1, like this. Okay, based on this, how can we see if this series converges or not? Well, if you imagine to do some integrals right here, can we integrate this right here? Sure, you can actually integrate this. If you would like, you can use integral test. But to use the integral test, be sure you graph the function x squared over square root of x cubed plus 1. And you'll realize that that function does not even approach 0. The truth right here is that we can just do the following. Again, this is the series that we're trying to do. But let me just go ahead and check the following. I'm just going to check the limit as n goes to infinity. Yes, we are doing the test for divergence. And you'll see just this part, which is the n squared right here, over square root of n to the third power plus 1. And of course, this right here is just a power situation. You can look at this and look at that. The 1 doesn't really matter. So this is the same as the limit as n goes to infinity. On the top is n squared, on the bottom. This is n cubed in the square root. The square root is the same, 1/2 power. 1/2 times 3, that's a new power, namely 3/2. Simplify the powers, you will know that this right here, this is gone, and 2 minus that, right, which is just 1/2 on the top. And then we have the limit as n goes to infinity of n to the 1/2 power. Put infinity to here, to the 1/2 power. This right here will be infinity. Well, infinity is of course not equal to 0. Therefore, this right here, what's the conclusion? Yeah, this right here diverges. And what's the reason for that? Well, we did a limit check right here, right? So, diverges by test for divergence. All right? So, don't just like use the integrals without doing check on that. This right here, you can just do a test for divergence. That's it. But if you did the integral, you will still end up with divergent. But the problem is that you technically cannot use the integral test because it's what? Positive, but this right here actually is increasing. Yes, you can also use the limit comparison test for this, but I'll leave that to you guys. Right? So I'll show you guys how to do your integrals for this one. Anyway, here we go. I'm just going to tell you guys that we are going to consider the function, which is f of x, that's equal to 1 over x plus square root of x. And again, in order for us to use the integral test, be sure you just apply a graph right next to it, and you will see the graph looks like this. X cannot be 0, so you get like a decreasing function like this, right? And just mention that the function is continuous, decreasing, and positive. So let me just put this down. Right? Well, let's go ahead and check the integral. Here is the deal. Integrating from 1 to infinity, and we are going to integrate this. So this is not really like an infinite series video. It's about the improper integral. All right, now, how do we integrate that? Partial fractions? No. But should we factor? Yes. This right here, we can factor out a square root of x. So when we do that, we will see this is the integral from 1 to infinity, 1 over, take out the square root, and then we can do u sub nicely. We will end up square root of x right here. And when you take out a square root of x from the x, you have square root of x. Because this times that gives you this x back. And then we add 1 right here. Right? So that's the factoring for that. And then we do u sub. Let u equal to this, and then that will be the idea. You may also try to let u equal to square root of x from here, and let me know how that goes, but I will do it right here, right? So I will go ahead and say, let u equal to this right here, which is the plus 1. Right? So square root of x plus 1. And we'll see du is equal to, differentiate this guy, we get 1 over 2 square root of x, and then that will be 0, so this is it, and put down dx. And I want to get the dx by itself. Let me just multiply this on both sides. So that's dx equals to 2 square root of x du. And now we will take this to the u world, and we will see this is equal to the integral. When x is 1, put it here. Square root of 1 plus 1, we get 2. So u will be going from 2. Put infinity to here. Then we get infinity in the square root, which is infinity plus 1 is still infinity. So u goes to infinity, like this. And then let me write down 1 over the square root of x stays, because it's going to get cancelled really soon. And then here is the u in the parentheses for that. dx is this part, so we just write down 2 square root of x du. So that's the integral in the u world. And then we will just cancel the square root of x very nicely. And now, to integrate this guy, we'll see this is equal to, put a 2 in the front if you like, integral, and we have 2 to infinity, 1 over u du. So this is 2. And then the integral of 1 over u is natural log of u. You don't need the absolute value, but because everything is positive, but I'll put it down anyway, why not? And then we go from 2 to infinity like this. And as you can see, putting infinity, putting 2. First we get 2 natural log parentheses, well, absolute value, infinity, doesn't really matter. And then minus, putting 2, so we get 2 natural log absolute value 2, like this. Well, this part is infinity, okay, just work that out. This right here is finite. Infinity minus finite, congratulations, we still have infinity. So, all in all, this right here is infinity, meaning that this improper integral diverges. Therefore, this infinite series also diverges. Why? Because we use the integral test. And that's pretty much the idea. And yes, you can also do the limit comparison test. If you want to do that, be sure you just use the sum as n goes from 1 to infinity of 1 over n. That's the divergence series you can use to compare with this. Now, number 77. A slightly interesting one? Not really. No, it's actually really interesting. Instead of the plus sign, we have a multiplication. So here we have n equals 1 to infinity 1 over n square root of n. Very nice. Okay, this right here is just exactly equal to 1 to infinity. This is the same as 1/2 power, so all in all we get 1 over 1 plus 1/2, namely 3/2 power. Take a look of this right here. P is 3/2, which is greater than 1. So this right here, it converges by the P series. Right, so that's it. That's it. But as we can see here, we have the nth root of e. It's okay, don't worry, because just as the square root, we can look at it as the power of 1/2, and the cube root is the same as what? 1/3 power, right? So here we can look at this as the e to the 1 over nth power. And let me just write this down right here for you guys. This is a series as n goes from 1 to infinity. On the top, it's actually just e to the 1 over nth power. Over the bottom is n squared like this. And here, how can we deal with this though? Well, imagine we are just dealing with integral. Can we integrate this? Yes, we can. So we'll just change this to the integral version and check the improper integral for it, right? So here we go. We are going to check the improper integral from 1 to infinity. And we have e to the 1 over x squared dx. However, don't forget to supply a function, right, the graph of the function on the side. And if you use a graphing calculator, just graph this right here. You will see there is an asymptote when x is 0, but it doesn't really matter because if you look at just this part, the function will be decreasing, right? So this is e to the 1 over x squared. This is the graph for that. All right, so it is continuous when x is bigger than 1, and it's positive, and of course, decreasing. So these are the 3 criteria. Now, how can we integrate this though? Yes, we'll do some u substitution. So here we go. We are going to let u equal to 1 over x right here. And we can just differentiate both sides real quick. Du is the same as, this is like saying x to the negative 1 power, bring the negative 1 to the front, minus 1 to the power. We get negative x to the negative 2. So that's negative 1 over x squared dx. And perhaps because we're the negative, then we just isolate the dx. Multiply negative x squared on both sides. We have negative x squared du like that. All right, and we can finish everything in the u world. So here we go. This is when x is equal to 1 to infinity. And if we take this to the u world, when x is 1, put it here, u will be 1. So be sure you do that. And when x is infinity, we put it here, 1 over infinity is 0. So that will be from 1 to 0. However, look at this part. We have e to the u's power, because that's 1 over x, that's the u, over x squared. Let me just keep it, because for the dx, let me put this down and I'll show you guys a cancellation. Here we have that, namely negative x squared du, like this, right? So now, I'm going to show you with my green pen in my pocket. Of course, we get the x squared cancel each other out, and here's the deal. We can bring the negative to the front, so this is the same as saying negative and then integral from 1 to 0, and we pretty much have e to the u du. And if you want to just integrate this and then plug in 0 first and then plug in 1 and subtract, and just in the end multiply it by the negative, that's totally okay. But remember one of the properties of integrals in general. If this is negative, in fact we can just switch the limits of integration. So I can just do the integral from 0 to 1, but this is a positive version now. So that's the idea. You don't have to do this though, but perhaps it's easier this way. Anyway, just finish this real quick. Integrating e to the u in the u world is just e to the u, and then we go from 0 to 1. In this case, we put in 1 and then put in 0 and then we subtract. Put in 1, we get e to the first power, and then minus putting 0, we get e to the 0's power, and we do the subtraction. But all in all, we get this is just e minus 1. So of course, this right here converges because this is the finite value for that improper integrals. And now we can go back here and say what? This right here also converges by the integral test. So I'll just write this down right here for you guys. The integral test. Like that, right? Also converges. We have cosine of 1 over e to the n as n goes from 1 to infinity. Should we just integrate this because we're in the integral test homework section? No, because in fact we cannot integrate cosine of 1 over e to the x power. So here's the deal. Keep in mind, cosine of 0 is equal to 1. And in fact, if we do the test for divergence, that's it, right? So that's exactly all we have to do. So here is the check. Let's go ahead and take the limit as n goes to infinity. And we're looking at the an part only, which is cosine of 1 over e to the n. And here is perhaps some of my work right here. Put infinity to here, we are looking at cosine of 1 over e to the infinity's power, like this. And of course, here is cosine, but e to the infinity is infinity, and that's on the denominator like this. And 1 over infinity is 0. So we're looking at cosine of 0, and as I said, this is approaching 1. So in fact, this limit right here is equal to 1, which is not equal to 0. And congratulations, we are done, because we can just come here and say, this right here, diverges, why? Test for divergence, good, by T, F, D, and this right here is it.